So, continuing from what we have done, now I can calculate out the, if I know the beam's radiation and I know this is the beam radiation watt per meter square, intensity of radiation, as I told you earlier, we express it, the unit is watt per meter square, joules per second per unit area. So, intensity is usually energy density. Intensity quite often, of any intensity when we are talking, quite often we talk in terms of density, energy density. So, here it is actually power, density power. So, IB is in watt per meter square, and that is the beam, direct beam radiation normal to the direction of the beam itself, normal to the direction of the beam itself, right. So, that is showing normal, and if it is falling on a surface, horizontal surface, as I told you already earlier, this is incident angle is, this is altitude angle, beta is altitude angle, and this is in fact incident angle for horizontal surface, which is zenith angle, same as zenith angle in this case. So, IH will be IB cos IH, that is what we said earlier. We have said, because the area, this area is larger, this area is larger compared to this area, this area is larger compared to this area, this angle is beta. So, normal to this is this and normal to this is vertical, like this I am interested in finding out this. So, normal to this is this, and this will be 90 degree minus what is happening, IB sin beta, IH, So, IH, so this is normal to this surface, this is normal to this ray, and this is normal to this ray. So, this is nothing but IH. So, cos IH, this surface will be cos IH, and cos IH is nothing but sin beta, 90 degree minus. So, that is what it is. So, on horizontal surface, if I know the beam radiation, I know the altitude angle, I can find out the radiation, right. Beta is altitude angle. So, if I measure, but measuring we normally do it on horizontal surface, because my pyranometer I will keep it on horizontal surface. So, therefore, I can estimate the beam radiation from there. But remember, this is all we are talking about, direct radiation. A pyranometer, unless I have blocked, I have some way to block the diffuse radiation, it will give me what we call global radiation. Because if I have a surface and it receives radiation, it will not distinguish whether it is a direct beam radiation or coming from skyward. For example, today outside, if you see outside it is all overcast, there is no sun's ray, but still you are getting some radiation, that is diffused radiation, that is diffused radiation. So, it will not distinguish between diffused and direct radiation. So, what is done is you actually have a kind of a strip, sort of a strip on top of the pyranometer sensing area, and this strip can be moving, which will block the sun's direct radiation, allowing most of the diffused radiation to come. So, normally two pyranometers are used together, one measures the global, which is the sum total of the diffused and direct radiation, other measures only the diffused radiation, because sun's ray direction, sun's radiation is blocked. So, difference between this gives me beam radiation or direct radiation. Okay. So, this is one thing. So, for any surface, of course, the amount of radiation intensity falling onto the surface is equals to IB cos I. Why? Because I is a incident angle, I is a incident angle, that is what we have defined. So, on any surface, it is for any surface, sun's radiation is falling like this, this is the incident angle is this. So, radiation falling onto the surface will be given by, or if it is a vertical surface, let us say radiation falling like this, normal to the surface is this. So, incident angle is this one, the amount of radiation will be given, or for that matter even for an incline. So, it will be given as same cosine law will be valid. So, IB cos I for any surface, cos incident here in this case for horizontal surface incident angle is IH. So, therefore, it will be IB cos I. So, if I measure horizontal radiation on horizontal surface, that multiplied by cos I divided by sin beta will give me the radiation that is received on any surface, which is maybe inclined or whatever it is, does not matter, but that is it. Because beam radiation multiplied by the cos of the incident angle will give you the radiation that is falling onto the surface. That is what we have seen in the beginning also. For I measured on horizontal surface, find out the beam radiation, relationship between horizontal radiation and beam radiation is given by this. So, measured one is horizontal radiation. If I know the horizontal radiation, incident angle and altitude of the angle of the sun for any surface, I can find out the solar radiation. So, that is radiation on any surface. Now, I said that it varies from day to day. What varies from day to day? The altitude angle from an azimuth angle, or it also varies from time to time of the day. Now, let us say at a given time of the day, 12 noon, let us say 12 noon is what? Solar time. What is 12 noon solar time? When the sun is right on top of your, it is maximum altitude. On a given day, it is at its maximum altitude, right. So, that is your 12 noon, it is at its maximum altitude. So, that is 12 noon. Let us say at 12 noon. Now, as I said, for any latitude, the altitude angle corresponding to 12 noon will vary from day to day, because only one day, even take let us say Tropic of Cancer, only on a given day it is normal, next day onwards it will keep on shifting. So, that we take account through an angle called declination, that we take account through an angle called declination angle. It is the angle sun's ray make with the equatorial plane on a given day, because this angle will be how much on 23rd June on Tropic of Cancer, on 23rd June, not Tropic of Cancer, on 23rd June, it is a equatorial plane. So, this is your equatorial plane, let us say. Sun ray is falling like this, sun rays, no color change, I want to change the color. Okay, this must be a change in color. Yeah, sun ray is falling like this, right. This angle we call as declination angle, right. So, what will be its value on 23rd June? 23.5, 23.5, and also on December same, only its direction change. In between, so declination varies from about 23.5 to plus 23.5 when it is in the north to minus 23.5. So, this is what we define as declination as, and I think I might have written, yes, that is right. So, at 12 noon between minus 23.5 to 23.5 is a function of day of the year, it is a function of day of the year. So, this angle, okay, this angle, I think I will come to this statement later on, but let me see if I have a diagram. Not really, no. So, it is a function of day of the year. Now, there are a number of empirical equations to find out d as a function of n, capital N, which is number of the year, number of the day of the year. I will give you only the simplest one. There are, because it is empirical again. Its angle varies in a periodic manner from 23.5 to 23.5. But if I want to, because days are also, you see, our calendar, we have a leap year also. So, it is 365 days, 6 and some hours, and there are some more complications. If you want to go to more details, it becomes more complex. So, I will be using a simple equation for declination with respect to day, and let me see if I go to the first equation, then I come back. Not really, no, let me see if I have the relationship. Not, I think I will give the formula, then later on I will come back to this formula. Now, I think if I look at this diagram, so I said that this is the declination angle, sun's ray is like that, and for any surface here, horizontal surface, its sun's ray is like this, let us say its latitude is something of this kind, right. So, 90 degree minus latitude minus declination is actually altitude angle of the sun, because altitude angle of the sun is between these two, horizontal plane and sun's ray. We will have more details of this, we will come back to this. So, latitude L is an angle at a location, we will come back to this and we will just do a little bit of geometry also. L is the latitude angle at a location subtended by the radius joining the location with equator at the center of the earth. I have already defined it, formal definition is here. Now, we define an angle to define the time of the day, we call it hour angle. We call it hour angle, right. Now, if I want to define time in terms of hour, how much 24 hours will be equals to how much angle it will be equal to? 360. Right, it will be equals to 360 degree, because every hour is 15 degree, it completes the whole cycle in 24 hours. We have defined all, I mean as a human being we have defined hour, in another unit it would be different. Traditional Indian unit it was different, Paul something something, what are those called, I do not remember them right now. There are other so, but the conventional time unit that we are using in SI units, that is second, an hour. So, we divide this a day in 24 hourly cycle. So, 360 degree corresponds to 24 hours, 1 hour corresponds to 15 degree, 360 divided by 24, 360 divided by 24 corresponds to 15 degree, right, it corresponds to 15 degree. Now, we take the starting point as 12 noon, we are looking at local time, local solar time, not the standard time. If you have standard time, then there is an axis shift, so you have to do the correction. So, 0 hour angle corresponds to 12 noon, and it would be I might take, I mean I can use a given convention. So, convention could be 50 degree for every hour from 12 noon. If it is 11 o'clock, then it will be minus 15, 12 o'clock it will be 0, 1 p.m. it is 15 degree plus. So, I can use that kind of a convention, right. So, that is called time defined in degree. So, hour angle is the time defined in degree. So, that is another angle which you will be interested in. Now, you can see this diagram, this is my north pole, earth rotates about this axis, sun's ray is falling onto this. So, normal to this one is the equatorial plane. So, this is the declination, sun's ray making this angle, this is declination angle. This is the point P, this is the point P. So, sun's ray is falling like this. Now, this is the angle normal to this surface, this is normal to the surface. So, the vertical will go like this. If I join a line from radius to the surface of the earth, that will actually represent the vertical at that point. Normal, the horizontal surface is tangential to this one. So, normal to the surface and sun ray, that would be normal to the surface as sun ray, that will be 90 degree minus basically horizontal and sun's ray, that is basically altitude angle. Horizontal and sun's ray, horizontal to sun ray, that is altitude angle, and vertical to sun ray, that is zenith angle. Vertical to sun ray. So, this angle is zenith angle, this angle is your this angle is your this is zenith angle, this is altitude angle, altitude angle normal to between these two. So, our angle is now earth rotates. So, there is a shift. So, our angle will be defined here, our angle will be defined here. So, it is in the equatorial plane, earth is rotating. So, our angle will be defined from 12 noon to later part. Let us see some more of this diagram, make it more clear. So, this I already explained to you, and this is showing same thing, declination how it is varying 23.5 to  23.5. So, if this is the north, this is the equatorial plane, This is a simpler diagram than 90 degree minus latitude. So, this is the sun's ray and this is then declination angle, makes it clear. And if I am interested in a point somewhere here, this is the latitude angle, this is the latitude angle, because it is also defined from the equatorial diameter. Now, I am interested in an, so this is my horizontal surface at that particular location, horizontal. So, angle between horizontal and sun's ray is nothing but latitude angle, angle between horizontal altitude angle, sorry, this is zenith angle, vertical, this is nothing but vertical radius to that point and extended that line, that is nothing but vertical, normal to the horizontal. So, this is vertical and this is parallel, this is sun's ray. So, this is nothing, this angle is latitude, this angle is declination, difference between them is L minus d is nothing but zenith angle. Zenith angle equals to L minus d, this is only at 12 noon. At 12 noon zenith angle is equals to latitude minus declination. So, altitude is nothing but 90 minus latitude and declination. Is this point clear? If not, just let me make it clear again. You see what I am saying is, this is my, let me explain it again, this angle. See, this is my north direction geographical, this is my equatorial plane, sun's ray coming like this. So, this is declination, there is no confusion on this. This is my location is this. So, latitude angle is this between these 2 points. So, this angle is nothing but latitude minus declination, latitude minus declination. What is this? This is vertical, this is sun's ray. So, angle between vertical and sun's ray is nothing but zenith angle, 90 minus that is altitude angle, that is what I was telling you earlier. So, it is at 12 noon, 92, altitude angle beta is equals to 92 minus L minus d. So, yeah, this we have already defined. Now, supposing I take sin beta, then this will be simply cos, and I can write it like this, and cos beta will be written as sin L by d. So, I can write something like this. So far I have not taken care of hour angle at all. So, at 12 noon this equation is valid. Cos of the altitude angle is equals to sin of the latitude, cos of the declination, this is simple, sin beta is equals to cos L by d, cos L minus d, and cos beta is equals to sin L d, because 90 minus L minus d, and sin L cos d minus cos L sin d, because sin L minus d can be written in this manner. So, at 12 noon this is simple relationship between altitude angle and declination and latitude is given by this. So, at 12 noon only. If I want to take hour angle, that becomes a little bit more complex, which we will look into. That is right. So, hour angle is time defined in degree, I can take that also into account. Therefore, beta is actually a function of latitude, declination and hour angle, latitude, declination and hour angle, right. Similarly, azimuth angle is also a function of latitude, declination and hour angle. Simple empirical equation amongst many complicated equations, this is one of the simple equation for declination. Simple equation is 23.45 sine of 360 divided by 365 multiplied by 284 plus n, where n is the number of days starting from 1st January, number of day in the year starting from 1st January, right. So, number of days counted from 1st January. For example, if it is 25th July, 26th July, then it will be 31 days January, 28 and not leap year, 28 days February, then 31 days March, n will be equals to something like this, 31 days March, and then April is 30 days, May is 31, June is 30 and plus 26 days of July, right. So, that is what it is. So, you can calculate this out when n is equals to 365, how much does it come to, n equals to 1, how much does it come to. Actually, it will vary between 23.5 to 23.45 to 23 point, around there, because sine of this angle will vary between it is 0 to 1, minus 1 to plus 1. So, south sometime in the it will be minus 1, because it varies from 23.5 plus to 23.5. So, 23.45. So, that is what it is. So, it is an empirical equation. There are more complex equations as I said, but we will be using this only. So, you can find out declination using this. Maybe I have a small calculation. Now, hour angle, as I said, we defined absolute time, true solar time minus 12, 15 degrees. So, sometimes we do often use it absolute values, not plus and minus. So, 15 degree hour angle both plus and minus, because if it is depending upon the angle itself, because cos of minus angle is as good as cos of plus angle. So, maybe it is related to that, and gamma is so actually incident angle can be written in this formula, but I think I'll go a little bit deeper onto this just for the sake of understanding. Supposing S is my wall solar azimuth, y, or it should be gamma, wall solar azimuth, then incident angle is given by cos beta, cos gamma, sin tilt angle, or no, solar azimuth, sin beta, cos gamma. So, incident angular function of altitude angle, wall solar azimuth, etc., we will derive them actually, we will derive them. For tilt angle, this small s is tilt angle, this is tilt angle, wall azimuth is not coming here, this is tilt angle. So, it is function of all this, and for horizontal surface it is simply cos I is equals to sin beta. We will go more details into this actually, we will look into more details into this, right. So, vertical surface tilt angle is 90 degrees, so correspondingly it changes. These are simple cases, more complex cases we will look into. So, when this tilt angle is 0, sin beta remains, this term goes away. So, cos I is equals to sin beta, cos of incident angle is equals to sin beta. For when S is equals to 90 degree, this term vanishes, cos beta, cos wall solar azimuth, that remains. This is actually should be gamma, most often I am using gamma, or y similar. So, we will deal with this a little bit more. Supposing, just for the sake of calculation, I want to find out beta at 2 p.m. true solar time on 22nd June at latitude 55 degree north. Now, why I have taken 55 degree north? Because this is same problem is given in Marcus and Morris's book. So, we can verify, that is why I have taken. Otherwise, for a scenario of Indian condition or tropical condition, I should have taken much lower latitude, but the formula is same anyway. So, beta and phi I want to find out. Our angle is 2 p.m. So, 14 minus 12 into 15, 30, absolute value. So, we can take, so 30, our angle is 30, n is equals to how much? 22nd June. So, 31 days, 21 days, February, March, April, May, 22, 173, right. Capital N is equals to 173. So, my d value will be, how much will be d? Declination 23.47, this 45 or 47, I think there is this empirical formula. So, there is I think 23.47, sin 360 by 365, put it here and you get 23.46, right. So, beta you have found out, and if you find out beta, declination you have found out, you can find out, well, you can if you want to find out at 2 p.m. as it is, you need more complex formula than the simple formula that I have given you earlier. So, let us look at that a little bit more in details now. So, in order to look into the relationship between altitude angle, hour angle, azimuth angle, declination and all that. Now, I want to find out altitude angle and the azimuth angle from latitude, declination and hour angle, because latitude defines the location, declination defines the day of the year, and hour angle defines the time of the year. So, sun's position I want to find out. Now, this comes from the principle of basically spherical trigonometry. So, the relationship I think I did not give you, or maybe partly I have given you, but if you want to understand that completely, then you got to look into this concepts of spherical trigonometry, a little bit more details. Now, we define something called a celestial sphere is concentric with the earth. A sphere, if I conceive which has got the same center as the earth, and its radius can be arbitrarily chosen, so that's what it is. So, in that, if I can define this, the geographical north on the horizontal. So, this is my horizontal surface, right, and this is north, this is south, this is east, and this is west, this is vertical, So, this is this is a celestial sphere with center as a center of the earth. So, this is the this one itself, this is the sun's path, this is the equatorial plane, Now, if I look at the earth from the center, I can draw a line towards the north direction, towards the north pole, and also draw a line towards east direction, east west and north south. So, these are this line, right, these are these lines, and this is a point in the celestial sphere itself. So, altitude angle will be defined like this. So, celestial sphere first of all is a sphere whose center is earth, its dimension radius can be anything arbitrarily chosen. So, in that sphere I can find out, because if you expand this, diameter can be very large. So, the sky volt can be included, somewhere the sun's position is there. So, I can locate the sun's position on the celestial sphere, and directions also I can consider along geographical directions also I can put in there. Let us see how it is. So, in this case O is the center of the earth. This is in this one O is, or maybe I have another diagram, this will show you better. Now, before doing that, let us understand a little bit related to spherical trigonometry. Compared to our triangle in Cartesian coordinate, a spherical triangle is defined by 3 arcs on the surface of the sphere. In planar triangle, I have in plane, there will be 3 lines which will close the polygon, and I have the triangle. Here I will have 3 arcs, one arc, another arc, and another arc. They will form a kind of a triangle on the spherical surface, and it is defined in terms of this arc is defined in terms of this angle. So, sides are defined in terms of angle subtended at the center, right, and also there is an angle between, two of those surfaces. From the radius, from the center, if I draw a line to one of those vertices, two of those vertices, then I can get a plane, and that is angle between these two planes, subtended between these two planes are the angles of the spherical triangle. Now, some of these 3 angles can be more than 180, unlike the planar triangle where this sum is 180, here it could be different. So, we will see that. So, I think we will look into the concept of spherical trigonometry, because that would give us proper understanding of all the angles that we are looking into.